Good morning, everyone. So where were we? I want to just jump into the lecture without any delays. Okay. Great. Okay, let me get started. Actually, before getting started, one of your classmates is self-isolating, and they have a problem. The laptop has died on them, and they need a laptop. So I'm going to ask the student to post on Piazza in case anybody living in Waterloo has extra laptop or a PC that they're comfortable with sharing with others. They probably would need the laptop for 3-4 days. So if you have a laptop, an extra one, or a PC, and you're comfortable with sharing, send me an email. I'll connect you to the student. I'll also ask the student to post on Piazza to see if there is anyone who can help. Okay, so let's get started. So I'm actually going to skip over some slides today because I'm a little bit behind. In what is coming in few slides, we're going to go through why we're talking about operating systems and why operating systems are interesting. Okay, so we're going to look into some trends and hopefully get some ideas about how operating systems have adapted to those trends. The first and the most important one is the trend in technology. So let me give you the gist of this figure. So for years, we have been putting a lot of transistors in our chips, and we have been doubling the number of transistors. While doing that, we were able to speed the chips also up until around 2005, where the performance we were getting out of our CPUs basically did not improve as we were expecting it to. The solution at that time that came to mind to architects was to put more processors. So this is where we started putting a lot of processors in our chips. So up to this point, most of systems were uniprocessors, and then after around 2005, people shifted their attention to multiprocessors. But unfortunately, as you can see here, this also hasn't worked that well because we haven't really been able to address the underlying problem, which is power. And what is not shown here is a trend that if you are now familiar with the industry, you probably have heard of, and that is specialized hardware. So if you've heard of tensor processors, so these are processors that we design for a specific task. As a result, they do that task very well, and they don't spend a heck lot of power. So we're at least able to speed up the specific application that we care about. And that's basically the trend now. You see a lot of specialized hardware being deployed these days in the cloud, in data centers. And the underlying reason is basically this figure. Okay, I'm going to jump on this. Yeah, so basically what you would expect today if you go and buy a multiprocessor is a system like this with a lot of power. So the takeaways from this is that we're still, decreasing the size of our transistors. We're now in 14 nanometers, 7 nanometers. But we're putting a lot of cores in each processor. And then we're also doing hyperthreading, which I'll talk about in the next lecture. Yeah. Okay, so another trend or another technology that you should be comfortable with to understand operating systems and how things work is the memory hierarchy. So the closest storage that you have is your registers. So they're very close to the CPU. They're actually on the CPU. Accessing registers is very fast, but you don't have many of them. You don't have megabytes of registers. You only have few registers that you can use. After that, you have L1, L2, L3 caches. So these are the caches that you usually see in modern processors. As you go towards the bottom of this list, so after the caches, we have main memory DRAM, then you have the local storage, and then you have the remote secondary storage. As you go towards the bottom of this, you get larger capacities but slower accesses. And then as you go to the top, towards the top, you get smaller capacities. However, you get a lot of performance out of them. So they're very fast to access. And this is very important. So one of the tasks that we will talk about is managing these caches. What exactly do we want to cache? What is the best thing to cache here? Because we don't have excess amount of it. It's basically very limited capacity. So we should be smart in what we want to cache. So usually our data resides in a storage, in a let's say hard disk or an SSD, and then we bring that data to memory, which is a lot faster than storage. But then from there, we can also cache it into L1, L2, and L3 caches and get a speed up by caching them. Okay, I got a question. How much of these trends should we know for quizzes? Is this part for context? Yeah, I mean, I'm just trying to give you context. I know you care about quizzes, and that is understandable. But let's focus on learning more than what comes or doesn't come in quizzes. If I say this doesn't come in the quiz, you're not gonna pay any attention probably. If I say, oh, I'm gonna quiz this. I haven't yet designed the quizzes, so I don't know what comes or what doesn't. But look at it as a trend to give you context for what is gonna come next as we see in the course. Okay. Great. So this is an interesting chart with some interesting numbers that, according to Jeff Dean, who is a chief engineer at Google, all engineers should know. But the gist of this is basically very close to the picture that we saw in the previous slide. So if you want to reference or access a memory block in L1 cache, it's going to take about half a nanosecond. And if you want to actually send a packet from California to Netherlands back to California, it's going to take 150 million nanoseconds. And you see everything in between. So if you do a branch misprediction, for those of you who know what that is, or then L2 is an order of magnitude higher access penalty than L1, and so on and so forth. And then you can see that main memory is here, basically orders of magnitude more more cost to access memory than the cost you pay to access L1. And then disk is here. So if you want to access something on the disk, that's probably how much it takes to read 1 megabyte from your from your disk. It's going to take 20 million nanoseconds. Okay, another trend that is very interesting, and it's getting more interesting as we go, is the I/O trend. So in this figure, you have on the x-axis you have the years, and then on the y-axis you have the values. So with the blue and red curves here, you're seeing network and disk speed. And by speed or throughput, what we mean is megabyte per second, how much data you can transfer per second. So these two are in megabyte. So you look at these values, and then it's going to be megabyte. The green one, however, is your DRAM, and the scale for this one is gigabyte. So don't look at this and think that memory is slower than disk and network. It's faster because this one is gigabyte. These two are megabyte per second. But that's not the point. The point is this gap that seems to be widening as we're going forward. So seems like what we saw with processors, that the speed up that we were getting with processors was stagnating or flattening. Similar trend seems to be happening with memory, or at least we're not getting as much as we were expecting out of our memories. However, our disks and network cards are getting faster and faster and faster. So this gap is widening. And that's something interesting to look for and to be prepared to manage when that gap closes altogether. Okay, here is another trend that is interesting. Back in days, you had like a building of computers, and in some cases, like hundreds of thousands of people were using that one computer in that one building because that's all there was. There was like 1 to 5 computers in the world, and everybody wanted to use them. And then look at the trend now that each one of us are carrying multiple computers at the same time with us. And like you're carrying your cell phone, inside your cell phone, you have a bunch of multiprocessors, a bunch of controllers, microprocessors. You have your watch, you have your laptop, you have so one user now owns tens of computers. Compare that to back in days where you had one computer and everybody was using it. We still have instances of those, like data centers, the cloud. You still have those instances. They survived. There is still a market for those as well. But these days we have all this spectrum, right? We have Internet of Things. We have cloud data centers. We have PCs and laptops. So this is also another thing that is interesting. And at the end of the day, you who are designing an operating system or a system management system, a management system, you have to know who is going to use your system, how many users you're going to have, for what scenario you're writing your system. Okay. So one of the big differences between operating systems now and operating systems in the past is it comes from this fact that about the number of users that we have. So back in days where you had one system used by a ton of people, a lot of people, the systems usually were batch systems. So what was the batch? What do we mean by a batch system? Basically, you wanted to keep the CPU as busy as possible because you had a lot of users. So even 1 second of CPU being underutilized was a big loss because you have users that you want to serve, right? So what happened was that you would have a queue of tasks that have been submitted to your system. Everybody would come in and submit their task or their job that they wanted to run. And then the operating system would just dequeue from this task and then run somebody's task and get it done, go to the next one, and basically streamlining this. Now, moving forward, we got to a case where pretty much you have, your system was used by you yourself, but then you had multiple applications at the same time. And then you wanted your applications to be interactive. You didn't want one application to wait for hours to be served. So systems moved to multiple users at the same times, but also multi-programming. So you wanted to serve applications seemingly at the same time, given that you have a uniprocessor, but you wanted this is where the operating system acts like both a referee and also an illusionist to pretend that we have as many processors as we are running applications, because all of them were it seemed that every one of them was working at the same time. Right now, if you look at how many processes you're running on your laptop, you probably have hundreds and thousands of processes and threads running, and you only have a handful of processors. So for all those processes that are running, they think that they have their own dedicated CPU running them. But in reality, it's the operating system sitting and then multiplexing between the processes and pretending that each one of them has access to its own dedicated processor, where in reality, it's like you have limited resources, you're just time sharing them. I got a question. So why do they call these things laws, like Bell's law? They're more like prediction. Yeah, they are more like prediction. It's just, it has been there. Like, for instance, Moore's law, which was about the slide that I showed you, how we are adding more and more transistors. They say it's a law, but it's really a prediction. That's a correct observation. Okay. The other trend that we have to be mindful of is the complexity of our application. So I think I have an example for complexity here, which tells it all. One software that we are most interested in this course is kernel. And you can see how kernel has become complicated and complex in years. Just looking at one instance, like this is just Linux kernel. On the y-axis, you have number of lines of code in Linux kernel, and then on y-axis you have time. And as you can see, there are a lot of lines of codes, and it's basically going up pretty rapidly. So the kernel itself is getting complicated, and that's one example of the complexity of our software. And again, that's important because operating systems are serving software. And when you're serving something, you need to know more about it. So knowing that your applications are getting complex, one implication of that, very small implication, when something gets more complicated, the chance of having errors and failures in that component goes up. So now looking at this figure here, it should be alarming that the one application, the one software that everything relies on, basically kernel, is getting more complex. So probably there are bugs in it, right? And that's dangerous because everybody relies on kernel. When you're looking at software or applications, if you don't have proper isolation and your applications are getting complex and buggy, then that could actually affect the system, that could affect other applications and the kernel itself. So what is architecture I386? We're going to actually, I mean, this is not an architecture course, but we'll talk about different architectures as we go. So the one that you mentioned is basically Intel's 32-bit architecture. The other one that we will talk about is the 64-bit architecture. Did I make a mistake? How do we distinguish between other and ARC-I? Okay, 386. I think you're asking about this figure. Let me zoom in. I see. So I was on right track to explain this. So x86 has a 32-bit architecture and has a 64-bit architecture. These are very mainstream, and most of the kernels support them. So that's the two you can see on top. I think there's also the other. So the other could be ARM architecture, could be superpower architecture from IBM, could be anything else. So you have a lot of different architectures, right? The one that you're working on, your lab, is an ARM architecture, ARM 32-bit architecture. Other examples, you could have RISC architecture, RISC-V architecture, for instance. So these are different types of architectures, and usually kernels should know what architecture they're running on. So you have code that is specifically written to deal with that type of architecture, processor architecture. So and that's basically what it is here. So basically how many lines of code are dedicated to deal with a specific things about x86 architecture or other architectures. I hope that answered the question. Okay. So again, this is basically one of the main things that we're going to see in this course. How can we make sure that we're taming complexity? We're not allowing faults and failures to propagate in our system. How can we isolate each application and each process so that if any fault happens, it actually happens within that and it doesn't propagate throughout our system. So this is going to be a main focus of this course going forward. Okay, great. I was able to finish this eventually. Now let's move on to one of the most important lectures of this course. Lecture 2. Okay. Is there any questions? Okay, Let's get into this then. What are we going to see? As a brief history of operating systems, which I'm going to move on so fast on. And then there are 4 fundamental OS concepts. Some of them you have seen in the past, and some of them are potentially new to some of you. But definitely pay a lot of attention. So this is one of the most important lectures, if not the most important lecture of the course, because we're laying down all the important concepts of an operating system. With regard to brief history of OS, I'll do my best to walk you through some of the important aspects of it. But for those of you who are interested, I have actually included some videos from YouTube. Definitely give it a shot. Watch if you're interested. One of them is about Unix and its history. BSD, I think I have a link for BSD, and then there is one complete web page dedicated to the history of operating systems, which is worth looking and spending some time on if you're interested. Okay, so the first part basically talks about the trend that we just saw in the previous lecture, where you had systems where the hardware was very expensive. You only had few computers and then a lot of users, and now today you have one user and a lot of computers. So that's basically an important factor, trend in technology that actually impacted how we design operating systems. And the implication of that trend, as I explained, was going from a batch system where you have a main queue of all the tasks that have been submitted by all the users, to a system that you were doing multi-programming. And then even with what multi-programming basically means is that you have one user, it has multiple programs, but still, all you care about is to run all those programs, to a system where you do time sharing between those programs. It's important to you to have low latency. You don't just care about utilizing your CPU all the time, right? If you look at your cell phone, it might be idle most of the time, but when you're using it, when you're interacting with your applications, you want them to be interactive. You don't want to click on an icon and take like a few seconds for the computer to respond. You want it to be really responsive. That's where we started talking about time sharing, and so on and so forth, right? Now, what you usually see when you look at archaeology of operating systems is that writing an operating system from scratch is expensive. You will get a taste of it in this course by writing your own operating system. You will see how challenging it is to do that job. As a result, usually new operating systems rely on previously written operating systems. You don't want to, you don't want to do all the things from scratch every time you write a new operating system. That's why usually the operating systems that we're using today, they have a lineage going up to years ago, and they just were built on top of each other, getting some ideas from previous generations, getting some of the implementations they didn't want to do again, and so on and so forth. So this is something to keep in mind. Usually when you look at a kernel, there is a history in it, and that's kind of in many cases unavoidable because you don't really want to go ahead and write 200 million lines of 200 million lines of code from scratch, right? Okay, so that's pretty much what I wanted. I mean, if you're interested, actually, I think I talked probably a little bit more last term, and the lecture is up on my YouTube channel, the same channel that I'm uploading these videos. So if you're interested, definitely take a look. But more interesting than what I talked about in previous term is the videos that I've put on the website. So if you're really interested, definitely watch those. Okay, now let's get to the meat of this lecture today. We're going to talk about 4 fundamental concepts of operating systems. And those 4 are threads, address space, process, and dual mode operation. I am expecting you to know threads and processes well. I still give you some, I will try to refresh your mind. But probably address space and dual mode operation is kind of new, probably, I would assume. Please like and subscribe. Yeah, maybe. I sort of don't. Yeah, I don't care if you like and subscribe because I'm not getting money out of it. But if you wish, do so. I think one venue that I cared about having subscribers was when I was designing the course and I really wanted to use my tablet to use the YouTube live event and to be able to write as I teach. And that option, basically live streaming from your mobile device, was only available if you had more than 1,000 subscribers. So I actually own another channel that I'm not going to tell you what it is. It's like totally unrelated to my profession. And that has more than thousands of subscribers, but I didn't want to use that channel to live stream my lectures. That one, probably nobody knows who I am. But anyways, I digress. Yeah, if you wish, like and subscribe, tell other friends of yours to subscribe so that I get above 1,000 so that I can use my tablet to present. Yeah, okay. Okay, so before getting into the concepts, let's quickly go through what happens. Share it regardless. No, I'm not going to share. It's totally unrelated to what I do for a living. Okay. Now, let's look at what happens at boot time when you turn on your computer. So let's we're gonna just at this point here's the deal. So the lectures that we're gonna see, we talk about operating systems, but at some point we have to talk about specific examples about architectures. Usually, as you will see in the slides, we will pick x86, which is the most common architecture used. But things could be different in other architectures, like ARM, like Superpower from IBM, like any other architecture that you might see. So to make that distinction, I usually mention that this part is a specific about x86. Okay, good. I bet he posts Super Mario speedruns. Can we start an internet campaign to get you? Yeah, that would be awesome. Get me over 1,000 subscribers. Awesome. Petition for others. Yeah, I like all those suggestions. You're awesome. Okay. I get tired standing. Okay, so there is this thing that you probably have heard, have dealt with. We call it bias. That is the first thing that runs when you turn on your computers. In x86 systems, usually we put bias on ROM, a read-only memory. So now you might ask, YouTube rewind to it. You're not going to let go, are you? Okay, so let's talk a little bit about this ROM thing here, that bias is stored on it. Start speed run when. Sorry, I don't get that comment. I'm gonna still publish it. Okay, let me get through this slide, please. So ROM, read-only memory, is expensive. It's very fast. It's very close to the processor, but it's expensive. And when you want it, it says it's read-only, but usually you can write on it as well. But writing to ROM takes a lot of time. Now, the first thing that your BIOS does is it copies a bootloader program from the disk to memory, and then it jumps to the start of that bootloader program. So from now on, so this BIOS was in ROM, but it copies everything on RAM, basically your DRAM, and now bootloader program starts running. So what does bootloader do? But bootloader knows where the OS kernel is. So it just copies the OS kernel to memory next, and then jumps to the OS kernel. And then OS kernel just takes over. So usually the first thing it does in Unix-like systems, it starts running the init process, and then you get a login app set up for your users to log in, and from there on, you know the story, right? Now, few questions here. First of all, why not storing the kernel on the ROM? So why do we need these two to first start? Why not just storing your kernel in ROM and start running kernel from scratch? So the answer to that is, well, kernels actually get a lot of updates as we go. But as we saw, ROM, it's very hard to write to it. And that is not something that we probably would appreciate. So that's one reason. Now, you might say, okay, why not load kernel instead of bootloader? Why do we need the second indirection? And the answer to that one is twofolded. First of all, what if you want to have multiple operating systems, not just one? So one of the things that the bootloader does, it recognizes that there are multiple operating systems installed, and it usually asks you, do you want me to load Linux, or do you want me to load Windows, for instance? So that's one. The second thing is that your BIOS only needs raw to read raw bytes from a given memory location, disk location. So it usually reads from address, let's say 000 to some address, and that's where you store your bootloader. It does not know exactly what is in that, so it doesn't know any structure. It just reads bytes and stores bytes on memory, and then jumps to the first line of what it has brought up. Whereas bootloader usually knows file system. And what do I mean by that? basically with bootloader knows files, knows directories, knows boundaries of files. It's not going to just read bytes without knowing what is in there. So bootloader usually knows file system, and that's another reason that we want to have that. So I got questions. Does bias the bias is copied to physical memory too? There's no need for that, right? It's already in kind of memory. It's a ROM, but it is a memory, so you can actually execute there from your ROM. I'm actually not sure. I think it can execute from ROM, but I'm not sure. So I don't know. I could check and get back to you. As far as I know, it doesn't. So it just runs on your ROM. Would the disk be the hard drive? What is the physical memory? Yes, so your disk is basically your hard drive or your SSD, your flash memory. Your persistent memory is basically your disk. And then what was the other question? What is the physical memory? The physical memory is your DRAM, your DDR3 or DDR4 or whatever DDR. You have your DRAM, dynamic memory. Okay, what is UEFI bias? It seems to let you select boot devices and stuff. I've actually seen it. For some project I had to deal with it. I don't exactly know what the difference is between this one. It had something to do with Linux, with Windows. I'm not quite sure. I can get back to you on that one. So what is the bootloader knowing the file system? Because it's so somebody's asking why is it important that bootloader knows the file system? So as I said, right, you want your bootloader to know how many operating systems you have, right, to distinguish that, oh, there are 2 operating systems installed. So which one do you want for me to choose? If it was just not knowing what is stored there, how is it going to recognize that you have 2 operating systems installed? So that's pretty much why. Who writes the BIOS for the computer? Is it the laptop? So usually the BIOS is written by the manufacturer of your motherboard, because it has a lot of hardware stuff that it has to do, recognizing all the devices that are connected to the computer. Usually when BIOS is working, you actually can use your keyboard, your mouse, and such. So usually is written by the manufacturer of your motherboard. Publish. Okay, we are loading bootloader in the DRAM, right? Yes. Is the entire OS booted into RAM? Wouldn't the OS be too big? No, you really don't need to load the entire OS or kernel. You could bring the code up, the entire code, but it would be as you said. So here's how you should put it. Usually you have services within kernel, so you could bring up kernel, and then you could start using different parts or services of kernel later on as needed. The other thing that we have is dynamically linking libraries. So if kernel also is using some libraries, we don't need to bring those libraries when we initially load the kernel. We only need to link them or have them when we need them. What exactly is physical memory referring to? Physical memory, as I said, is just your DRAM. Okay, we updated the information in the we update the information in the bootloader when we update the iOS so that we don't have to update bias as it is in ROM. Sort of. I mean, you still can update bias, but the process is different and it takes time. I myself have updated my bias, but updating bootloader is a lot easier than updating your bias, and a lot less involved, if you wish. Okay, let's get going. So, as I mentioned last time in the last lecture, the bottom line of the operating system is to run programs. We want to run programs, and that's basically what we want to do. We want to have, as a kernel, the minimum footprint. We shouldn't be using most of the resources. We have to allocate resources to the users. And that's pretty much why in your lab 1, we're asking you to minimize your footprint. Any data structure that you're using is going to spend space, like it's going to occupy space. So try to minimize that so that you can give that space to programs that want to use it. Now, usually this is what you see. So operating system resides in memory. Let's say this is physical memory. We have operating system loaded. This is kind of like a a simple example of like we coding something and then compiling it, and then when it's time to run our applications, we would expect the operating system to load our application to memory, and then we would start running it. I actually will have lectures on different parts of this figure. So this is just high level what's going to happen, but we're going to actually dive deep into what exactly this means for the operating system to load this executable image to memory and start running it. But high level, this tells the story pretty much. Once we bring up all the static part of our image to run, we usually also want to allocate stack to our applications, heap and a stack. Usually what happens is that we put the stack on top and it grows downwards, and then the heap grows upwards. And usually in between, you have some free space. We will see that other things would come in between heap and stack. And this is one important thing. So the registers that we have in our processors, these are usually what we mean by context of our application. So if you remember the first lecture we had, you bring everything in memory, but you want to run them on processor, and the processor takes copies of what it needs into the registers, and then it works with those registers, and then when it wants, it saves registers back to the memory. So when we're talking about the state or the context of a running program, what we usually mean is the state of memory and these registers inside the processor, what we have on them, and what the content of those registers are would tell us the context of our running program. How does updating bias work on a ROM? So as I said, you still can write to your ROM. It's going to just take more time. Usually, if you've done this process, you turn off your computer, and then you turn it on. And when you're about to enter bias, the manufacturer has a few keys that if you press, you would go to that mode. Hopefully, you have a flash disk with the new image for your bias that then can be read and then written to your ROM as the new image. And if you mess up your bias, then your entire computer cannot come up again, or you would need to write the bias again. Okay. So when we say that the operating system transfers control to a processor, to a process, what we basically mean is there's this one register in almost every processor called PC, program counter. And wherever that program counter is pointing to in memory, that would be the next instruction that the processor will execute. So if the PC is pointing to an instruction in a thread or in a program, then that basically means that that program has access to the processor at that time, because we're running the instruction for that program. Okay. So let's look at the cycle of running instructions in our processors. I'm not going to dive deep into this, but very high level, I want to lay out what happens when you're running a program on a processor. Let's assume that the data for your program and your instructions are already in the memory. Operating system has loaded them in the memory, so they are there. And let's say that the PC is pointing to one of your instructions. So that's the setup that we have at this point. Now what happens next? So what we do first is we fetch that instruction that PC is pointing to. By fetching, we mean we read that instruction. So we access memory, we read the instruction that PC is pointing to. Then we decode that instruction. And by we, I mean the hardware usually does that. So it parses what that instruction does. Is it an add? Is it a multiplier? Is it a multiple? Is it a divide? Is it a shift? Whatever that instruction is. Is it a branch? So it decodes what that instruction is. Now, once you decode, you execute that. Now that you know what that instruction is, you start executing that instruction. Usually, if it is arithmetic, you usually have an ALU that does the arithmetic, and you usually involve some registers. So you have to add 2 registers, you have to divide 2 registers, the content of 2 registers, or multiply the content of 2 registers. And then once that is done, you have a result here stored in another register. And at the end of the cycle, you're going to write your result back to the memory, probably. Depending on what the instruction was. So what happens next is we usually update PC at this point. PC now is going to point to a next instruction to be executed. Now, this function next here depends, right? So if you're just going through your program sequentially executing instructions without any branches, without any exceptions happening, then next PC is 4 bytes from the original PC. So you just add 4 bytes to your PC, and that would be PC next. If the instruction that you just executed was a branch instruction, then PC has to point now to the result of that branch, whatever we have to jump to. If an exception happens, for instance, which we will talk about exceptions, now you have to go and deal with that exception. So PC is going to point to where it has to execute next to deal with the exception. And then we repeat. That's basically what happens. Now, given all of this, let's talk about the first OS concept, threads. This is a unit of execution in our systems when we talk about threads. And the context for a thread, as I alluded to, is basically the registers that you have in your processor plus the context of your memory. right? When your thread is running, it means that the registers in the processor now have a copy of the data for this thread, depending on which registers you're using. So I have to be careful here, right? Because your thread might not use all the registers, but if it wants, then all of those registers are in the service of that thread. So the thread has access to all those registers. And basically we would say that the registers, whatever they have at the time of running the thread, that's the state or the context of the running thread. So what registers do we have? That would depend on the architecture. So in an x86 architecture, we have a set of predefined registers that our threads can use. In an ARM processor, that is different from x86. In an IBM processor, it's different. In RISC-V processor, those registers are different. So what registers do we have? That depends on what architecture we're running our program on. The other thing is, usually how we use those registers is dictated by the compiler. So compiler usually uses those registers. When you're programming C++, you usually don't have anything to do with the registers. You have your variables and such, and it's the compiler's job to map them to registers and use the registers. The other thing about registers is that we usually have some conventions on what register is used for what. Like back in days, it was the convention was, was followed by almost everyone. These days, if you follow that convention, you're a good citizen. If you don't, it's fine, as long as your program, your system behaves as it's supposed to behave, you're fine. Okay. So my hope is that at this point, everybody knows what threads are. Hopefully you did do multi-threading in ECE 252. You have, you should know concurrency very well. You should know how to create threads, how to join on threads, how to wait for a thread, how to delete a thread. At least the API you should know pretty much well. Okay, now let's move on to the second OS concept, which some of you might not know, and that is address space. So what do we mean by address space? So it's a set of accessible addresses and their state. That's basically all that is to it. So set of addresses in memory and their content. What is stored in those addresses, and that would be address space. Now, to put that into context, let's define some other things that you might mix up with address space. The first one is physical memory. So what do we mean by physical memory, as people ask? So this is a physical memory is a storage medium. So it's a device that we store data on. That's all that is to it. Usually when we say memory, we're talking about our DRAMs, right? There are other types of physical memory, especially nowadays. Like they're thinking about other technologies to use when it comes to physical memory. But in a common, in your laptop, in your PC, we're basically talking about DRAM. That would be physical memory. When switching between threads, does the OS save the entire stack heap of a thread to perform a context switch? I feel that this is slow and inefficient. If so, where does it save them to? That's a good question that I was going to talk about when we talk about processes. So all the threads within a process, they all share the address space, which we're about to talk about. Now, stack and heap are parts of the address space. So all the threads share this. So we don't need to save it. All we need to save is the state of processor, which is basically the registers. So when we switch between threads within the same process, all we need to save is basically the registers. Things would be different if you're context switching from a thread in one process to a thread in a different process. So we'll talk about that. Okay, so physical memory, then physical addresses. That would be the set of addresses to access physical memory. So now if you have in the labs, we have 1 gigabyte DRAM. That basically means that we can only address 1 gigabyte of memory from a certain address to a certain address, as you might have seen in your lab manual. So that would be your physical address space. Those are the addresses that have corresponding bytes in your physical memory. Now there is another thing called virtual addresses. Now this would be the set of addresses that are available to any program that runs in your system. Now, how do we distinguish between the two? Now, if you have a 32-bit system, like the ones that we have in our labs, that means that your program, if a program is running on your processor, it has the ability to address anything between 2 to 0 to 2 to 32 minus 1. So for a 32-bit system, that would be 4 gigabyte of data storage, or it's 4 gigabyte of addressable bytes that your process can potentially address. Now, you should now see the difference between the two. Let me give another example. If you have a 64-bit system, that means that your process that is running on your processor can address anything between 2 to 0 to 2 to 64, and that would be a humongous amount of capacity. This is like 18 quintillion addresses. So in a 32-bit system, that would be 4 gigabyte. In a 64-bit system, it's going to be 18 quintillion addresses, which obviously we usually don't have as much physical memory corresponding to that. So there is always a difference between the two. And that's where operating system comes and sits. So operating system sits in between your process and the actual hardware and does the mapping. So if the process says, I want this address, operating system says, oh, this means this physical address. So there has to be a mapping. Let's say in our case, in the lab 1, we have more virtual addresses because our system is 32-bit system. So each program can produce any address between 0 to FFFFFFF, right? But then in reality, we only have 1 gigabyte. So we have to just sort of only use that 1 gigabyte that we have in our DRAM. In, in a, let's say you have a system, is a 64-bit system, and you have 4 gigabyte memory, your processes can potentially produce these many addresses, but obviously you don't have them. So you have to map and say, oh, this area you cannot actually access at all. So if you access this, segmentation fault. You cannot access this. Now this range of addresses, I'm going to map it to this range of physical addresses. This range of virtual addresses, I'm going to map it to another virtual addresses. And that would be address translation, which we will talk about. It's going to be a big portion of the course that we're talking about address translation. Do most computers use byte addressable memory? Yes, usually. So now let's look at where things are stored given a program. This is a typical C program. Usually this whole thing, these are basically instructions. So if you look at these are like some bytes, right? Your binary code is stored here. Let me take a step back. I'm talking about virtual address space of a typical C program. How, when you compile your code, how things are organized in your virtual address space. This, we're not talking about physical now, because as I mentioned, there has to be a mapping from virtual to physical. That is a different topic. We'll talk about it later. For now, let's just look at the organization in virtual address space. So focusing on virtual address space, the address space that the program sees and thinks that that's how things are, because the program doesn't see what OS does. But from the program's point of view, I got a question. I'm confused about how we can have more virtual addresses than physical. As I mentioned, so you could have, here's an example. When you have thousands of threads in one process, in reality, you don't have thousands of processors to run those threads. So basically, that's where operating system sits and time shares between those threads to use the processors that are available. The same thing with memory. So your programs could think that they have unlimited, basically in a 64-bit system, 18 quadrillion addresses. That's almost on, infinite amount of memory. So your programs could think that they have infinite amount of memory available to them. But then operating system sits in between and just maps those to what is exactly available, which is 4 gigabyte. And now you could imagine that if you have, a lot of programs and each one of them are using a lot of memory, well, you only have 4 gigabyte. So you have to space share. So if then you don't have enough memory, you have to kick somebody out, send them to your secondary storage, and then run whatever you have. And then once you're done, you can bring them back, basically swapping processes out of memory and then back to the memory. So that's the art of the operating system, to provide this illusion that you have infinite amount of virtual memory, whereas in reality, you have limited physical memory that you have to manage, which again, we will talk about in details about memory translation. That's what we mean when you get virtual memories from your processes and then translate them to physical memory, which is what you have. I hope I answered that question. Okay, so what else? Any initialized variable that you have, global variables, static variables, anything that is initialized goes here, right above your binary code. Any uninitialized variable goes next. again, we're talking about organizing these inside the virtual address space. Then next thing is your heap. Every time you allocate things dynamically, those are allocated inside your heap. That's where they are organized in your virtual address space. Whatever you have as environmental variables, environment variables come at the top. Anything that you define in your functions, variables inside your functions would go on the stack. And as I mentioned, stack grows downwards and heap grows upwards. Usually you have free space here. And that's basically where you put your dynamic libraries, as I mentioned. So you might have libraries, right? You don't want to write your own printf or whatever. You don't want every user to do those things. So you have those libraries, but then you don't want to always statically link all those libraries, because you might actually not use those libraries. You might have if switch cases and branches and stuff. You might not end up using a printf. So what's the point of binding a library to your virtual space if you're not using it? So you will wait until you want to use it, and the moment that you want to use it, you basically link that here. What time is it? Okay. Let's keep going. Now, let me look at, just briefly explain what happens with a stack, because this one is also important, as we will see when we talk about context switching. You should have an idea of what happens with your stack as you call different functions. So what we're going to see in this example is this piece of code. So you have function A. You put libraries in the stack. No, it wasn't on the stack. So the libraries come between stack and heap. So heap is growing to upwards. Stack is growing downwards. In between, you have free space. You dynamically bind your libraries to this free space. So given whatever you have free at the moment that you're using that function, a library function, you find a space that is available, and then you bind your library to that state space. So are the dynamic libraries linked at compile time? No. So dynamic libraries are usually either linked at the time of launching your program or at the time of using the functions in that library. Yeah. More to come on that as well. Okay, so usually, okay, I was explaining. So we're going to see how this code runs. We have function A, we have function B, and we have function C. So these are the definitions, declarations. And here I'm running A1. So let's say PC is here. PC program counter is pointing to A1. So we want to execute A1. And let's say the arrow here you see is going to be a stack pointer. So pointing to the top of our stack. And our stack is going to, as you saw in previous slides, is going to grow downwards. I got a question. Does this mean having a lot of libraries would decrease available stack and heap space? Potentially, but again, don't forget, in something like a 64-bit system, your virtual memory, you could assume that it's infinite. That's how big it is. So yes, in reality, if you you might end up in extreme cases, you know, exhaust all the addresses that are available to you, but in reality, that never happens. You have a lot of virtual memory, your programs. Okay. Now, what happens with the stack is when some of this stuff that I'm going to mention are architecture dependent. So different compilers, different architectures do it differently, but hopefully you get a gist of what should happen and what usually happens. Again, there are some details that are architecture dependent or compiler dependent, but the big picture is what you're going to see here. How much time I have? I have 4 minutes. Let's see if I can get it done in this 4 minutes. So the moment you call the function, you're gonna store at least 2 things on your stack. The first thing you're gonna store on your stack is your return value. So where am I gonna go once I'm done with this function? So you stored your return value. That's here, return. So if once we're done with A1, where should we go? We should go to the next line, which is exit. So the return address becomes exit, and we store that on the stack. The second thing that we store, and that would depend if you have variables or not. Sorry, if you have inputs or not. So this function has an input, which is 1. We usually push this also on the stack. So here we call the input that A accepts is TMP. So we say TMP equals 1, and we put that in the stack. So we push these 2 on the stack, and the stack pointer now points to the top of the stack. Now, what do we do next? Now, next thing we're going to do, we're going to jump into our function. So at this point, now PC will point to the beginning of A. So here we have a branch. We're going to check temp less than 2. We look at the top of the stack. Temp is 1, and it's less than 2. So we're going to go and execute B. OK, now we reached the second function call. Again, we have to push stuff on the stack. There is no input, so we don't need to push any input to B, but we still have to push return address. Where are we going to return after B? We're going to return to A3. So we're going to return to this line. So we push the return value, which is A3, on the stack. And then we jump to function B to execute it. And we see that it's a function call. So again, it doesn't have any input. We don't need to push anything for the input. But what is the return address? It's going to be B2. Once we're done with C, we have to go to B2. So that's what we will push on the stack. Here you see we push return B2 on the stack. And then we jump to C. Now here we're in the C, in function C, we're going to call A. Now again, this one has an input, so we're going to push temp equals 2. And we are also going to push the return address, which is going to be C2. So we'll push temp equals 2 and return equals C2. And then we jump to function A. Now, this time we're going to check TMP less than 2. Now, to know what TMP is, we're going to look at the top of the stack. So the TMP top of the stack is 2. And 2 is not less than 2. So we're not going to do anything. We're going to go to printf. So at this point, we printf TMP, which is 2. So we print it. Then we go to A. So here we want to return. So we're done with this A function. Where should we return? This is a question. The answer is saved on top of the stack. So whenever we want to return, we look at the top of the stack, see where we should return. And here in this example, C2 is the return address. So we return to C2. Then again, we are returning. So we look at the top of the stack. It says B2. We return to B2. Again, this is a return. We look at the stack. Where should we return? A3. We go to A3. We have a printf. We print And now we have A4, another return. Again, we look at the top of the stack. We see the return is exit. So we jump to exit. OK, so that's pretty much what I have for today. Let me see. There's another question. Shouldn't the temp equals 1 and return equals exit be switched positions? So again, that would be very architecture dependent or compiler dependent. It doesn't really matter. I guess you got the gist of it. They have to be on top of this. Like the order could depend on many things. But what I meant was they're on top of this stack, and we're going to look at them on top of this stack. OK, so that's pretty much it. Thank you for everyone who attended the lecture, and whomever is going to look or watch the lectures online. Take care, be safe, and talk to you on Thursday. Bye-bye.